Hello everyone. This is Micah with Silicon Valley Global News, and also with the Neurolace podcast. And I'm here talking to Jules Urbach. He is the CEO of Otoy. The inspiration for the call was we recently had some epic news from Siggraph, and even following Siggraph on Nvidia's RTX, and also Otoy. So now Octane is integrated into the two top game engines, Unreal Engine 4 and Unity. One of the talks that Jules was interviewed by Nvidia at Siggraph, and he was really sort of startled and surprised by the fact that we now have real-time ray tracing on a single GPU. Is that correct? Did I interpret that
Oh yeah,
correctly?
yeah. It was a great interview, and it was one of those cases where I've been championing the cause of ray tracing hardware for a while. I mean, I was first exposed to that possibility 10 years ago at Siggraph when I was on a panel with a company called Caustic Labs, which was later acquired by Imagination Technologies, and they had really early ray tracing hardware, and it looked promising, but it wasn't powerful enough to really move the needle or do anything. And when they got acquired by Imagination Technologies, which was the company that ended up powering the iPhone's GPUs really up until last year, and unfortunately they went out of, well, they got bought basically, but Apple basically stopped using their GPUs, and that cratered the company. I was concerned that ray tracing hardware was like the electric car, or the car that runs on water. It would just wither on the vine. But we had tested the Imagination ray tracing hardware 2 years ago, and the Siggraph, we announced that, hey, we're going to ship Octane on this thing. It's a game changer. It's 10 times faster than the compute cores for ray tracing, and therefore path tracing, which is what we use in high quality visual effects for rendering. And I think that Nvidia was keeping this really quiet. They've been working on this thing for almost a decade, and we got let in onto the secret of that once the hardware was like almost to the point where it was about a year away from shipping. We got the development hardware. We rebuilt as much as we could of Octane as everyone on the experimental RTX hardware, and we had basically one implementation of stuff that we built on Vulkan, which is an API for computer graphics that was able to fully leverage those ray tracing cores, and we were seeing 8 times the performance of exactly the same generation card from the Pascal Nvidia generation, and it's very rare to see a 10 times improvement in speed in overnight in one instance. And there's still work to be done. I mean, it's so new. We talked that even with the year of advanced work that we did, we still have probably another 6 months before we can start shipping products that absolutely tap into the full power of those ray tracing cores. But the other part of that interview that I gave to Nvidia was that there's no doubt in my mind that the next decade of computer graphics, if not the next 20 years, is going to be defined by ray tracing hardware at the foundational layer, the same way that GPUs have just basically made 3D graphics, a commodity, even on our phones. We can play Fortnite on an iPhone.
So,
and I think that.
So there's been a lot of people, like I've shared a couple articles on this topic, and I really wanted to point out the fact that ray tracing is going to make a huge difference in how we experience virtual reality, and it's coming with this generation of cards, the 20 series RTX cards. It's going to change virtual reality. We're going to have people are going to be able to figure out, and this is what I'm telling people, but I'm telling people we're going to be able to understand a scene. We're going to be more immersed in the scene because the things like the reflections and the shadows, they will give you a sense of realism and a sense of immersion that we haven't had in VR before. But I tell people this, and I get this skepticism back, and they say, well, there's no way that we can, VR has to run at 90 frames per second, and you have to render the entire scene in real-time ray tracing. You can't, like that. Maybe I'm trying to argue you can use it as an effect. So I wanted to dial back from the hype a little bit and get a sense of the realism from you of how is this real-time ray tracing gonna actually affect our VR experiences, and do you expect to see new headsets coming this year or next year? What do you think the reality is in terms of the industry for VR and AR?
So I think, yeah, I mean, I'm a big believer. I just answered a Quora post like yesterday about this very question: is ray tracing, real-time ray tracing, great even RTX a gimmick? And it's not. I mean, it's so there's two parts of the rendering pipeline that are fundamentally transformed by having this kind of hardware in consumer cards. Shipping pretty much everywhere. I mean, the low end, the high end, everything's going to have ray tracing ASIC. That's even on the lower end 20 series Nvidia cards. first thing that you could do with that in VR is you can trace primary rays. And we were showing at the Siggraph booth, we could do 4K 120. So, I mean, that's, that's already, and that's easily doing 4K 120 with path tracing, with shading and everything. If we were just doing primary rays, we just wanted to essentially do foveated rendering, do all these tricks that, you don't have to work and render the thing twice. So we can do all that stuff without using traditional rasterization on these RTX cards. And even on one of those things, you could drive any existing VR headset and just switch from rasterization to path, to ray tracing. I think it's a big leap for a lot of game engines. I mean, one of the reasons why we've integrated Octane inside of Unreal and Unity is that, those engines have been built for a very long time on rasterization, and we have a great relationship with both companies. I was talking to Tim Sweeney about, Unreal and Brigade and Octane, all the things. He's like, well, the first step is clearly for us like hybrid, where we use traditional rasterization the way it is now, nothing changes, but the reflections and the shading are improved by ray tracing hardware, because that's low-hanging fruit. So all of the RTX demos that Jensen was showing for games typically, have that improvement in quality, from that. But that's really, that's almost nothing. That's really almost missing the true value of this, which is that if you go one step further, which I think we'll be able to deliver to Unity and Unreal Engine users right off the bat, is you can switch to complete ray tracing of the scene. So, immediately scene complexity, like forests can be rendered and everything. I mean, anything that Octane can render, even without the shading, for any film, like feature films like we did for Ant-Man and Wasp and the like, can be dropped into VR, and one or two of these RTX cards can power that. And even headsets that have, frankly, even 4K by 4K per eye, if you ever were to go that further, you can imagine things sort of progressing to that level. The RTX hardware can keep up with that, and you can start to skip a lot of the hacks and a lot of the problems that, one, held back scene complexity and visual fidelity, just because you had to render everything with triangles, not rays of ray tracing, light, and also things like anti-aliasing are solved, depth of field gets solved. A lot of effects ray tracing just solves correctly without having to hack it. And that's double the case in VR, where you can just render those rays. Instead of doing two renders and doing a low res one and using foveated rendering to mix those, you can just use ray tracing to basically do a heat map and just send more rays to the parts of the viewport that are looked at by the eye. And that's something you can't do in traditional rasterization, and it would be very expensive to do with that RTX. The second thing. Sorry,
okay. I'll let you finish.
So yeah, the second sort of boost from this whole RTX GPU ecosystem is not just the ray tracing hardware, but also the tensor cores and the FP16 floating point operations on there. So we have our own AI denoiser, but frankly, the stuff that they're showing at Siggraph for real time is really good. And so being able to do real time denoisers that are AI based or machine learning based, that can clean up shading noise that we have when you're doing really high quality ray tracing or path tracing, that also becomes a lot cheaper and a lot faster on this generation of GPUs. So combining those together, you end up really getting very close to solving, basically the rendering equation. In other words, all the laws of light and physics you need to drive VR in real time. And I think that it's going to take new content to drive that. I mean, just converting your Unreal Engine raster game with better reflections with RTX is easy, and it can look great. I mean, look at that Star Wars demo that they did. But there's a deeper and more, frankly, a much higher quality option that is just going to probably take 6 months to maybe 9 months to really get in the hands of game developers. And we're trying to do our part in that by providing, Unity and Octane are free together, and we're going to make Octane and Brigade inside of Unreal also very inexpensive. So we want people to develop content in that, and we're working on a real-time ray tracing system that, while it obviously will be able to go to the distance with RTX hardware, it also, if you go into our Siggraph, you'd see it's running on an iPhone, and we can do real-time ray tracing on that device and on Intel integrated graphics. So we've decided we were going to solve this problem for everyone and everywhere we can, but there's no denying that, like, when you're going beyond just doing it at 1080p, if you want to go to 4K or you want to do this for a VR headset or even, AR, that ray tracing hardware is a game changer. And so the idea is that we will bring, through just the two integrations we have in these game engines, we'll bring the entire cinematic pipeline that the film studios use for rendering movies, and we'll bring that to real time, and we'll bring that to VR. And then it's up to the VR headsets then to come up with higher resolution, higher frame rates. And,
so that's actually something that a lot of people are really astonished by, is that the real-time ray tracing is revolutionizing the movie industry in addition to the game industry. And you're promising that we're going to be able to hit 90 frames per second at 4K resolution with some of the with with titles that look as good as existing VR titles today?
Yeah, I
Or do
mean,
you think we're gonna have to
hopefully better. I mean, that's the point.
Yeah.
Hopefully, when ray tracing, you do something better. And there's, I mean, just like ray tracing, you can do it the hard way. You can brute force unbiased rendering, which is what Octane does. But there's also the same tricks that you have in games. If you want to pre-compute part of the scene and still do ray tracing, it'll still look really, really good. And in fact, many movies use that very same technique. Not all movies are done in Octane. Octane is the laws of physics, computed. It's like you can still do shader tricks and stuff like caustics and stuff in renders like Arnold, which are used in many films. Arnold also is moving to the GPU, which is great. And I think that the quality will definitely go up. And the things that you can do with ray tracing hardware are not necessarily super obvious right at day one with the launch of these cards. I mean, that's why I think maybe people aren't getting how big of a deal this is. But I think it'll be pretty clear for both on the cinematic, film side of things, where you can really do real time and have that film quality, and also, of course, for immersive, HMVs and the like.
So will developers have to shift away from using polygons and maybe start in order to really maximize the use of these new cards? Will they need to start modeling in voxels or light fields, or what does a developer have to do to?
No, it's on the content side. On the art side, nothing really changes. I mean, the only thing that so in Octane, there's really almost two paths, and RTX only accelerates, by the way, one of those, which is polygons. Like, it's still the only thing that the ray tracing hardware really does accelerate is the rendering of triangle meshes. And the thing that you can do in Octane for films is you can take something that is like a hair primitive, things that aren't necessarily easily turned into trimeshes. You can still turn them into trimeshes, and that's what you can do in any game engine. You can turn everything into a triangle soup, and you can send that to the ray tracing hardware, and it'll be much faster. From the art pipeline, if anything, it's simpler, because artists have to go, sometimes they start in a much higher quality version of what they would do for a cutscene or a film, and then they have to figure out how to reduce that quality to get it into a game engine. And our work, I mean, really half of the work we're doing with integrations into these game engines is not just the render, but also the art pipeline. Like, you can take something that you've created in Cinema 4D or Maya, or right for a Marvel movie, which is they use Cinema 4D and Octane, and for Elastic, which is the company that did the titles for Ant-Man and the Wasp, and you can just drop that into an Orbex package, which is the interchange format we open sourced for Octane, and you can drop it into Unity and Unreal, and you can then, with RTX hardware, you can now render that quality basically in real time. And that makes it easier. You don't have to basically come up with two pipelines. You can stick to one and start with the highest quality version to begin with. It's more intuitive and better.
So I went back and I watched a talk that you did at Siggraph in 2015, part of Lightfield talk with a bunch of other Lightfield talks. It was a really great series of talks, and I'll link them with the article that's going to accompany this. But I really wanted to sort of like go back to light field capture, which is how I first heard of your work. And it looks like at Siggraph that Google has basically reinvented the wheel with their light field capture. They basically redid what you did back in 2014.
I should point out that the employee that worked, Paul Dvevic, who's now doing that project at Google, worked with Otoy and was one of the co-creators of Lightstage and worked with us for 8 years. So he's a friend of the company, and he actually was part of that project that we did in our office. So he basically rebuilt that. You're right. He basically rebuilt that at Google, and they've been experimenting with it, and it's super cool. But that is basically, that's the exact, pretty much the same thing that we had been doing with the spinning camera. The improvements with having 16 GoPros and an ARC is probably makes it faster, which is great. But is exactly the same thing.
Well, the astonishing thing was they went from 16 GoPros back down to the spinning camera rig that you had. So they went up to the 16 GoPros, and then they reduced it back down to the two camera sort of thing. Except you only had one camera that was active, and they had two cameras that were active. So
yeah.
But it was interesting to see that sort of big circle. But talking about light field and so from trying to fill in the gaps in the light field is where the concept of AI denoising came from, that then became the concept that became the technology that enabled real-time ray tracing?
So they're all sort of separate pieces. For me, light fields, I mean, when you look at really where light fields end up, it's not even so much the capture, because for me, the real value of and even the work that Paul did and we did together when we were building Lightstage. I mean, all this came out of our Lightstage work. And Lightstage is more than a light field capture. This is what we do for high-end films. Like when we scan in, all the actors for an Avengers movie or, one of these big tentpole films, and we do this every week, every day. Like all the DCTV shows or Lightstage captures. We don't just capture a mesh and we don't capture a light field. We capture something more than that called a reflectance field, which gives you all of the ways that light bounces off that surface. So you essentially don't have to be an artist and write shaders for skin. You have the pore level details, you have the way light bounces, and that's really important for mixed reality as well as for films. So one of the reasons why we didn't go deeper into light field capture and push further even on that experimental thing that Paul ended up doing at Google was because really we want to get into, we want to be able to capture what we capture on a light stage in, basically in real time, and make that something that is consumable inside of Octane or inside of the art pipeline, because that's, if you're just capturing a light field, you're actually, while it is better than RGB in depth or maybe stereo or pano, it's really still very, a very small subset of the data that you want. What you want is you want a CG recreation that can be dropped into a renderer and treated like a CG object that matches the real world. And for that, you need to capture materials. And there is a lot of work that we're doing where we're looking at, we have the light stage to capture ground truth. Our AI denoising work, all the AI stuff we're doing is mostly speed up rendering to make it so that the rendering that you would get out of a ray tracer, path tracer can be done in a tenth of the time. The AI can just finish the work. You don't need to finish the simulation. The AI can figure it out in pieces heuristically. And capture is very similar to that. So our work at light stages, we have we have 800 lights. We can capture perfect holographic representations of people, but you have to bring them into a big stage. What we've been trying to work on, and what we've shown almost every year at not just Siggraph, but GDC and others, is we can take 120 frames per second stereo camera, which is going into phones these days, and we can pretty much use a little bit of machine learning plus some simple lighting patterns that are much less than what we do on a light stage, and we can start to get this absolute perfect live capture of reality. And that's really our goal. And AI will play a role in that. There's no doubt that capturing AI is super important, and we have to get that to work in real time, because otherwise AR and mixed reality will never look right. And that's something that I discovered, frankly, when I was looking at the Magic Leap device, which I got to test. What struck me was that nothing was really being relit, because I think your app on the Magic Leap platform has to request being able to capture the world around you, but things like that are really important. So what we were showing at Siggraph on the phone basically is able to reconstruct the scene from the phone camera, and then we're doing, we have a little mini version of Octane, we call it Octane Light, that is designed to basically do the minimum amount of ray tracing, so you can have objects that are mixed in reality live on your phone, and cast shadows and have reflections and just look great. And in order to do that, not only do you have to render and denoise, use AI denoising to get that to be the highest possible quality, but you also have to do some sort of scene reconstruction and do that live, and do it frankly without depth sensors, which is what the Magic Leap has that, and some other devices like Tango had that. But the iPhones just have two cameras, and they use basically pretty good computer vision algorithms, including after machine learning tricks to get that sort of information into ARKit. But all these pieces, I can't even imagine VR, frankly, existing in the future without pass-through cameras that allow you to switch to AR mode trivially, in which case you're back to the same problem, which is whether you're seeing the real world through your eyes and there's an overlay like Magic Leap, or, it's something like, I think what Oculus was talking about, and probably, who knows when it'll be out, but things that basically have camera pass-through where you actually are recording through two cameras, what's in the field of view, and you could do AR, you could blend that with VR. Like that kind of stuff is super interesting, and I feel like that requires everything to just be upped in terms of its quality and its setting. So AI is important for scene reconstruction, it's important for object segmentation, it's important for physics, and it's important for making high quality rendering work in real time. Ray tracing hardware is a big boost, and I think that the other crazy technology that I'm seeing where RTX is really important is kind of where, as referring to light fields, is being sort of it's more of a visual description of light. It's basically saying all the rays of light that make up both your left and right view for depth, but also things like depth of field that you see in cameras. All that stuff is essentially something you could emit from a holographic display if you had something like 4,000 DPI, and you had some sort of filter on top of it to guide the rays of light. And even Paul and even us as everyone wants to build a structure holodeck or get to that point, and it's possible. We basically probably the displays are kind of getting there. They're 4,000 DPI displays are not impossible. There's companies that they're out there working on it, and from our perspective, we actually are looking ahead of VR and AR, because I think that if you can have a glasses-free experience emitted from a table or a wall and that becomes sort of the fabric of buildings and services and furniture and offices and homes, and sidewalks going forward. I mean, that is going to be a lot easier to consume than putting on a pair of glasses. And I've tried some of the smallest and lightest weight glasses, and I think that's something where ray tracing hardware is like absolutely critical to make the holographic display panel at that resolution run in real time. Like it'd be very difficult to do that without ray tracing hardware making that 10 times faster. And because it's 10 times faster, we can now drive holographic displays probably in the next 6 months with this kind of speed in real time.
So I wanted to sort of jump off the deep end in terms of science. I was at this at a talk last night about they were talking about so Mary Lou Jepsen has this company. She's creating a new device that does I guess it's called functional near infrared spectroscopy. One of the technologies behind it is photoacoustic microscopy and photoacoustic tomography. And these are basically, and there's some other technologies like ultrasound encoded optical tomography. But basically, these are new kinds of medical imaging technologies that can be combined with things like electrical impedance tomography. And what it means is we're combining light and electricity and sound to image the brain in new ways. And we're basically creating a light field of what used to be an X. Well, we still use X-rays, but there's new X-ray tomography technologies too. But basically, all these technologies can be combined to create a light field of a person's brain. We can do a whole mouse brain. We don't know the full depth of what we can get. So I'm kind of like interested in like, there's all these people having these conversations, and I go to these really great conferences, but there's not a huge amount of talk about using the sort of AI denoising or really using deep learning at all. It's almost like there's a huge opportunity to figure out if real-time ray tracing, we're predicting what should be there can be medically accurate. In terms of helping to model the brain, helping to model brain activity, ionic flows of activity, the flow of ions and the electromagnetic field of the brain. That would be very interesting if we could begin to accelerate that research in medical imaging by basically combining the light field that we're trying to render with some of this AI denoising technology or real-time ray tracing AI. And I wonder what are the key differences between the AI that's involved in real-time ray tracing and the AI that's involved in denoising, and if it would be useful. And maybe you can speculate as to whether this kind of AI, how accurate this AI can be, whether it could be medically useful.
Yeah, so I should probably provide almost like a breakdown of how AI is used even in Octane, and because there's different AI libraries, just like you have different filters in Photoshop, and not all of them could be used. AI assisted rendering, I mean, we went through all the different things that are slow in rendering. We applied AI to fix them. So the first thing is when you do rendering correctly, it's noisy. It's just like when you take low exposure, there's a lot of noise. You need light to gather, and you need to finish rendering to get a properly clean image if you're doing really high quality photorealistic rendering. So AI denoising just finishes the render, and you're essentially trading compute for guesswork, but the AI is so good that it's looked at enough finished renders to know how to finish any arbitrary view. And we built that ourselves. NVIDIA's built that in optics, and that's absolutely fundamental to rendering. Like it's an AI layer you add to rendering. We also added something called, well, it's pretty straightforward. It's just AI upscaling, which takes a low res image and scales it up in a way that you can't do with a normal like bicubic filter or anything like that. It does recreate the edges, and you have spatial resolution or even temporal resolution added, which is why you can easily go to 120 or 240 from 30 frames a second. NVIDIA actually showed a great version of that working. And then there's other stuff where it's like you can start to figure out like what is the, if you have a piece of an object or a scene, can you finish the actual scene layout? Can you figure out from a photo what the actual geometry of a forest is and actually create the scattering of leaves and trees and all that stuff? And that's deeper, that's further out, but it's still something that is really interesting. And I think that is kind of where AI and rendering really do have a lot of cohesion. And then there's stuff that's really more for humans to be creative with. I mean, having AI that essentially like takes a simple stroke of your hand and then creates all this stuff that's augmented based on your history of how you paint or how you do stuff in quill or medium or tilt brush or something like that. Those things are really key tools of the future for sure. But and I also wanted to talk a little bit about light field rendering and baking. So for me, light fields are a shortcut. Like, we don't have all the time in the world to use AI denoising and rendering. With ray tracing, like, light fields were a way to render something into a light field. Is you're just basically generating a digital hologram, and then the hologram can be looked at from any angle, and you're done. And it's so cheap and inexpensive that you basically can, at the very least, you can run this on low-end hardware like a phone. You can also use the compute cost and ray tracing power you do save on other things. So that's where I see light field rendering and being super useful for games in real time without oversaturating the even the hardware that we do have. Even a 10x of speed up in ray tracing hardware is something you can easily use up if you're doing really complex light transport. What you're describing, though, with sort of this imaging of the brain as a light field or volumetric asset is super interesting. And I think I was reading one of your posts where I think maybe it was you, that was looking at the rendering of that in the VR headset, and that feedback loop where you're seeing what your brain's doing is probably some sort of kernel of an interface of the future that I've been thinking about for a long time. So I think this area of research, and activity is super interesting. I mean, there's a lot of talks about having thought-powered, experiences or input and the like. And of course, if you can see what your brain is doing, there's a lot of research being done about biofeedback loops and how that can be, open up and unlock all sorts of things. But I think that the fact that you can actually visualize that in VR and AR, and frankly, yes, ray trace it, which is way better than, you can take volumetric data sets and you can ray trace those. That's what ray tracing is really great at versus doing it in triangles. That is, to your earlier question, that's the one thing that you can bring in fire and volumetrics perfectly into ray tracing, and that'll look great. Unfortunately, RTX hardware doesn't do volumetrics. I mean, you can still add it in there; it'll still be fast, but you still need to use the compute cores to render that. But when you're seeing your own brain and you're thinking stuff and you're seeing your brain do things, I've spent years thinking about what that can mean, and I've been waiting for the foundational pieces of what we're building on the rendering side, on the ecosystem and platform side. And what's fascinating is that there's a lot of work that you can imagine being done with AI, looking at what that even at that feedback loop and filling in some holes and details to create things that frankly probably don't have great vernacular or words to describe how they work. I mean, we know that they're important tools for potentially for input or for content creation or who knows, more stuff. But yeah. I think that's you're scratching at the key of something, surface of something really, really, really fundamentally important for the future. I know it, and I think that's why you're on that too. That's great.
So one thing. So I'm leading a meetup every week. It's called Neurotech SF, and we have successfully connected an EEG device to WebVR to an Oculus Go. So that was kind of cool.
Yeah.
We got, so now.
That's great.
And so perhaps because of that, I'm one of my friends or connections is going to enable me to have access to an electrical impedance tomography machine. So the second phase of the goal is to I'm also acquiring some. Another friend is donating some or sponsoring me to give me some depth cameras. We're going to get a few Lucid cameras, and these cameras are going to enable us to create a volumetric video. And we're going to be collecting volumetric data of a person's mind with our electrical impedance tomography machine. And I want to do, I'm going to use this, I'm looking at this, I wrote about this 3D crosshair convolutional neural networks so that I want to try to do object segmentation on the volumes of data that we're getting from our electrical impedance tomography and on the volume of data that we're collecting with the 3D cameras. So I can begin to correlate so that we can have the AI begin to look for correlations between a person's brain activity, the volume changes, and the volumes that they're seeing in the world around them. And this is, just a big experiment. We don't have we have 4 Titan 5 graphics cards in the cloud, but we have to somehow stream that data up into those into that cloud and then back in real time. And so a person's going to, and then we're also going to be running this through VR so people can see their medical imaging, so we can correlate that. So with VR is very useful is you can correlate whatever the user is looking at or whatever their head is pointed at with their EEG. Actually, that's probably our next step is we're going to correlate what they're looking at with EEG. But eventually, we're going to be correlating the EIT with what they're looking at with the volumes of data that we're going to be representing in VR. And then VR also allows us to isolate, isolate other, random signals from the environment. So we're isolating a person from, so that we can begin to look for how a person's brain changes in response to that specific content. And the other idea is you can also look at how two people have different, how their brains are responding differently to the same piece of content that they're immersed in. So the point what I was getting at was going back to doing object segmentation on 3D volumes of data. It seems like, because we're talking about light fields and we're talking about volumetric capture and we're talking about so I haven't really seen, I think another area where this technology that you've been working on could be really useful comes to self-driving cars. All the self-driving car companies that I know of are, to my knowledge, and I don't know, obviously I don't know what's going on inside these companies, but on the outside, it looks like they're all using, basically two-dimensional slices of data streams. You get a lidar stream, you get these two-dimensional camera streams, and you're running two-dimensional convolutional neural networks on them. And I wonder at some point if it would be useful to start actually creating a volume of data first, and doing semantic segmentation on this volume, and doing upscaling this, so you could. I'm trying to think of, how. Because I'm trying to think of how rendering can really help solve the problem of self-driving cars. Because one of the issues, I guess, is so I said the self-driving cars, do they need to become self-aware networks? Do they need to become aware? Does a car need to become aware of itself? Does it need to have the thinking here is that there's this book by Peter C. where he talks about how that his theory of what the consciousness is for, it's a higher level information pipeline that exists to help us solve problems that are too big for the unconscious mind to solve. And so that's really, he sees it as sort of as an additional point, like when you get a computer that's powerful enough to solve those logistical problems, it would be a conscious computer. So that's why I'm like, well, is that where we have to go with self-driving cars to really get to the level 5 car? And do we need to have a light field render that we can? Because I asked the CEO of Nvidia if we are going to need a self-aware self-driving car, and he said that he didn't want to build a black box. He wanted to have every component basically, understood separately, so so that they could understand what was going on in the car if something wasn't working. But I think you could render what a neural network is doing, and so that's my thinking. I don't know if you have any thoughts on that topic, but.
Well, I definitely would defer to Jensen on the self-driving part. And he's obviously, NVIDIA is doing some crazy stuff in that field, and Tesla up until recently was using NVIDIA GPUs all over the place in Teslas. But I don't know if a car needs to be conscious. I think, frankly, people can drive and almost be unconscious and still almost by rote do the right thing, have sort of serious, it's sad to say, but you have almost the reflexes and everything can almost be trained like muscles, even for things like driving. And it doesn't necessarily require you to have, the same consciousness that we do. So I don't know if you need consciousness for the car. So if you have existential philosophical decisions, which sometimes you have with cars, do I run over the school children or do I save the driver? Even there, it's clear that you can program what you want the outcome to be in those scenarios into the system and get that. That is basically pre-decided. But the issue with rendering is that it's not really everything. Even for Otoy, we're not just a rendering company. We have capture and we have streaming and we have some other higher level things, which is basically the entire feedback loop from those things is basically what you really do need to solve for any system to become probably what we want it to be. If we're going to, let's say, recreate a perfect representation of reality, or if we're talking about, brain machine interfaces, it's you have to capture the world, you have to render it or edit it or understand it, and then feed that back into a way that the the interface, probably with a human in the middle of it, hopefully, can do something with. And that's why the company is divided into these three parts. Sometimes those parts are hidden and people look at just the rendering. But the capturing, the rendering, and even the streaming, whether it's, as you're pointing out, if you have 5-10 views in the cloud and you've got a VR headset that's not on the cloud, you have to combine those two. And a lot of the technology that we've built does that. It solves that problem for you. And that's kind of where we see ourselves fitting into this ecosystem, is we build these tools that solve some of the harder problems. But in terms of what's interesting, you brought up a point, which is what does rendering really do for AI? And there's if you look at some of these things where they simulate like the evolution of like jellyfish or multi-celled organisms, and you can see them basically be pushed onto land and then they grow limbs and all this stuff. I mean, take that to its logical conclusion, which is right all the way up to the simulation theory, which is if you basically simulate everything in the physical world to the point where, well, we don't know, it's so granular, the entities in it are covered. You can imagine basically creating life that evolves and grows and learns in an environment that's basically the same as ours, but can be accelerated, and you can have shortcuts, you can do all sorts of things. And so that's why, this simulation theory that I guess Elon was one of the people who made it popular, where, if you just imagine a video game or VR getting to the point where even if it's still a pair of goggles, but it just looks absolutely real and your eyes are fooled, and, then you figure out touch and other stuff. I mean, you come up to the scenario of like, are we AI running in a simulation, and how do we prove that we're not, or how do we, figure out what that even is and isn't? And it's a fascinating problem, but we're probably going to, we still have work to do before we actually can get to the point where reality itself is digitized so convincingly that one, cars can understand it the way we do, naturally, versus, with rough approximations. But yeah, I like there's something you can render in a simulation. The data itself is actually less interesting without the source that generated it or how it was captured.
Going back to 2015 at Siggraph, the first of the 4 talks on light field, one of them was, I believe, the gentleman you mentioned earlier, who's now at Google, and he was saying that basically, our eyes are capturing a light field. We have 2 points or two. I mean, your eyes have lots of different cells, lots of different that are responding to light.
There's lots of receptors. Yeah.
That's right. But so the idea is, what I've seen is that it is research going back into the 1980s on neural networks that can be used as signal processors. It seems very plausible that in looking at Jack Gallant's work, that he basically created a movie that was with MRI. He had someone watching a movie, and he had the machine watching their blood flow and the movie, and they trained it like that, and the machine just watched the blood flow, and then it pulled a movie. It recreated a movie from just the blood flow. And so the idea is, that basically what we're seeing is video. What we're seeing is a light field that our brains are constructing. And this was an idea that I saw.
Yeah.
And so if we're creating a video, but then it seems like we're creating a video, but we have that, the ability to learn from this video, but we're also rendering it. And I'm thinking about Google's Deep Dream and the, there was a huge story at Siggraph about the deep fakes or deep, they're able to like recreate an actor or recreate a person, and you could make that person. And so the idea is that, so for me, like what does rendering bring to AI? It seems like those are, if we're going to talk about creating an artificial, sentient mind, it seems like that, our minds have neural networks, but we're rendering, and the rendering is then being processed like it's in a feedback loop with the AI, where it's rendering, it's crunching what was rendered, and it's rendering on top of that again, and these are the feedback loops of the mind, I think. And so at some point, I think that your technology leads towards, you're already combining AI and rendering, and that seems to be like you put that in a feedback loop, and you eventually have a mind.
Yeah.
And so that's
and it's funny because I mean my and AI is I mean it's one of these things where as a product, I mean you have to be I want to release AI that's useful like right now this year, but it's the stuff you were talking about where you can recreate a movie, or you can I was reading about another, I think it was in Japan or something, where maybe I don't know if it was the same researcher, where you could basically figure out the letters that you're thinking about But again, sort of scanning the back of your head, and you can almost get like a 16 by 16 black and white pixel representation of what your brain is seeing or visualizing. I mean, you take that to its logical conclusion, that is going to be essentially, I mean, the stuff with neural lace that Elon's talking about, I mean, the bandwidth back and forth to the brain is not going to necessarily be through goggles on the eyes. There's some deeper stuff going on. And I think that you're right. Also, that's, consciousness and how we experience things and how an AI might experience things. We don't render the same way that a computer does. I mean, we don't even see the world the same way a camera does. I mean, our eyes like move around, and we basically build an image by, our eyeballs like scanning things very quickly and then coming up with a, with sort of a complete picture in our brains. And what our brains see, even if we see a light field, like even if a light field is being which is how you see convergence and depth of field and all that stuff in your eyeballs, even if that goes into these receptors and our brains are trained to figure out what that means, it's still, when we're seeing it inside of our minds, it's still something that is, we have no idea if people see this blue the same way. There's even tests where, people didn't have the word for the color blue in like certain continents, ever hundreds of years ago, and they don't see that color the same way we do. They don't see the sky and plants as being different shades of different colors. They see it as different shades of green. Like your brain gets trained, and because of that training, it can absolutely process the same physical cues very differently. And so what we're rendering in our brains, even just visually, may not be, it may have identical sources from the real world, but it may just feel different to different people, and maybe, it's segmented. If you're talking about object segmentation and how we process it and analyze it, that becomes different. What's interesting with an AI is that you don't have necessarily those limitations. I mean, you can basically just keep rebuilding AIs that think and look at the world in different ways. And even a modicum, even if it's a philosophical zombie and it's not true AI, the ability for it to process and do stuff and kind of act the way that humans would with that information and do more with it is fascinating. And I think we're going to get to the point where, and Google stuff this year with, those digital assistants that were on the phone that sounded real, like you're going to get to a simulated person, an AI, that even one that they can make decisions that look human, long before you get to the true like consciousness of a machine, which is still something like we don't even fully understand our own consciousness perfectly, I think, and so it's just, we're in for some fascinating years ahead, but AI and rendering are inextricably linked together, because truly AI needs to render. If it's going to simulate anything the way we do, it's the ability for it to do that is really powerful. And we can do it in a way that the human brain almost can't. Like the human brain can't render perfectly like a photograph does, or CGI render does, with the precision that we have. And therefore details and things that an AI could do visually or pick up on and stuff, cues that are there, which is what AI is already good at, could be augmented in ways we can't even begin to imagine. And that's why the next 10 or 15 years is so, it's just exciting, from the, artist and creative perspective and philosophical perspective as well.
Awesome. This is going to be a lot of great food for thought for folks when they listen, they have a listen. So thank you very much, Jules Urbach, the CEO of Otoy.
Thank you so much. It was always a pleasure.